Hi everybody. Welcome to session 6, the last of the Python class. I am really grateful to all of you. This experience has been really lovely as I learned how to use Python myself, and I hope that along the way I've had some useful things to introduce to you from the language itself. It's an odd language in a lot of ways. So many other languages make use of a lot of the curly braces, for example, to show what loops, what parts are inside the loop and what parts are outside. The kinds of commands that are available are a little bit different. I for one am very accustomed to using arrays in my programming, and switching over to using lists instead has been good, but it is different than what I'm used to. So I hope that we've been able to uncover some of the mysteries that might have tripped you up if you were just trying to learn on your own, and that today we're able to show you something that changes your opinion yet again about the language. I've put up one slide here. I just have this one to talk about. But I wanted to describe, to forecast for you what today is all about. One of the great, most powerful features that Python has to offer you is a very large set of very powerful libraries for dealing with all kinds of advanced functions. We have been dealing with FASTA files as though they are just text files. But of course, FASTA files are a very common file format for bioinformatics. So in the course of today, we'll be looking at Biopython, a library that a lot of people in bioinformatics use. I'm giving you a couple articles here. The one about NumPy, is it NumPy or Numpy? Numpy? Yeah, I mean, I grew up watching a steady diet of Disney movies, and so I think of Grumpy the Dwarf. I think this is Numpy, the library.
I also thought about it, and then when I asked them to fix it on the one server, then it was NumPy.
NumPy. Well, let the purists say it how they will. To me, it's always going to be Numpy. Okay, so Numpy, I've given you a DOI reference here. This is a very compact URL for giving a permanent location for a journal article. But one of the things that you would discover if you follow that link is that you are looking at an article by somebody from Stellenbosch University, I believe from one of the engineering departments, talking about how amazing NumPy is for dealing with large sets of data. Now I've noticed that here I say it has arrays for efficient computation. It's intended for scientific computing, so it's going to be very powerful. But when I say arrays, I'm kind of underestimating what you can accomplish with this, because NumPy or NumPy allows you to track data structures that are, well, let's imagine first off a one-dimensional array, right? So you have, say, an integer, an integer, an integer, an integer, an integer, just a long line of these, and maybe you set up an array of 10 items. That would be a one-dimensional array. But we're very frequently working with matrices, right? So you may have both a column of these integers and rows of integers as well. So in this case, you would have a 2D matrix of values. Now, probably some of you are still reeling from your experiences back in algebra classes in high school, where you were dealing with matrices and computing inverses and normalizing and so on, all kinds of very frightening stuff. Yes, matrix math frequently shows up in that realm. So that can be kind of stirring and amazing, but I would point out that you're not limited to two-dimensional matrices when you deal with NumPy or NumPy. You can get all the way up to 32-dimensional data structures of these integers. So you can accomplish some rather daunting computing tasks with the very flexible structure that NumPy, I don't know if I can say that, but NumPy can accomplish. So feel free to support the paper by your colleague here at Stellenbosch University and click the link, have them build up ad revenue or something. That's not going to happen. Okay, great. Biopython is a very, very helpful thing. Now, I know many of you have learned a bit of R along the way, and you probably remember learning a bit about bioconductor. Everyone remember bioconductor? Some really heavy functionality in there. You can do some serious bioinformatics with bioconductor. Well, the relative of that for the Python programming language is called Biopython. So Biopython is a large set of bioinformatics libraries It is part of the Open Bioinformatics Foundation Framework. I can't remember which one. What's the F stand for? Foundation or framework? I don't recall off the top of my head, I'm sorry. But in any case, it is a large collection of open source bioinformatics researchers who try to add to the functionality that everybody out there can benefit from in bioinformatics in many different languages. So the OBF supports not just Biopython, but also bioinformatics tools to support you if you're programming in C, for example. So once again, we have a paper here that describes in very short form what that's about. I believe that's just a 2-page paper, but it's useful to get a brief overview of what that language offers. Now, one of the reasons why I'm dragging NumPy, I'll try to say it, that we're bringing NumPy into this discussion is that we've been talking about vectors of counts or lists of counts. How many times did this amino acid appear in this database? But very frequently, we're dealing with numeric values of a different kind. So today, we're going to take advantage of Biopython to give us information about our sequences that we couldn't easily get when we were treating them as line after line after line of text file. And we will be then using some functions from NumPy to characterize that. So when you have a distribution of numbers and you want to evaluate it, how would you go about doing that? Okay, so with that, I'm going to drop us into the text. You will see that our import line has gotten more and more complex over time. So we already had sys, collections, and matplotlib pyplot imported. We're now going to add numpy here on the fourth import line. We need to make use of its functions for minimum and maximum and for medians and so on. And we're also going to import Biopython. But I would note that although the library goes under the name Biopython, the Biopython library actually includes a kind of a subsidiary library called Bio. All right, so we had to install Biopython, which in turn gave us access to the Bio library, and the Bio library has within it the SeqIO library. So we're not going to grab all of Biopython, but rather just the SeqIO part. So when you see IO in the name of a class, what does that relate to? We have one vote for the moon of Mars. No, it's not Mars. Oh my gosh, I just totally made myself look like a bozo on YouTube. I'm so sorry. Io is actually a moon of what? Oh, no one in the room. All right, well, we have some sci-fi fans. I'm sure that, hey, you can comment on this online. Let me know in the comments to this YouTube video which planet Io is a moon of. If I'm not mistaken, it's Jupiter. Is that right? We have a no from him and a yes from him. All right. Well, if we had Gerard here, he could settle the bet for us. But for now, we're going to say it's Jupiter because I say so. All right. That's fine. Great. So we are going to import from the bio library just this SeqIO part. So IO represents input-output. So sequence input-output objects make it easy to deal with FASTA files. Great. I've increased our FASTA Sniffer version to 0.5. And I didn't mean to pop up that menu. And now we're going to continue on. So this stuff is unchanged, all unchanged, all unchanged. So we have a file name. Now you will note that we've started with a couple oddities here. So we have changed from using the open command, which you recall we used to open a particular file name in read mode and create a file object from it. We've now changed that from an open command to SeqIO.parse. And we are giving it a file name, this FASTA, that part is unchanged, and we're specifying that this file name is an object of type FASTA. It is a FASTA sequence database. And the software will know, because we've told it this is a FASTA type file, how to parse it. Now, parsing is a term that computer scientists use a lot, but we often fail to identify what exactly we mean by this. So parse means to encounter a stream of characters and interpret it in some way. So when the software sees a text line starting with a greater than symbol, its parser is going to say, this is a description line. I should treat all of this information as though it's formatted for a description line. If it sees a line that does not start with a greater than symbol, it's going to treat it as a sequence instead. So the parser handles all of that. Now, you'll note that yesterday's code puts a try and catch around the open command. However, SeqIO parse doesn't actually do anything to the file except say, this is our target. So down here, in the part where we actually make use of that object, we're going to create sequence records that are drawn from the FASTA file. So the FASTA file is understood not as a whole bunch of lines, line after line after line, but rather a whole bunch of sequences, sequence after sequence. So our old for loop in yesterday's code was going to go through each text line in the text file and say, what do I need to learn from this before moving on to the next text line? But this for loop isn't making stops like that. It's only going to execute once for each section starting with a greater than symbol, in other words. So where before we had to go through maybe 10,000 lines of text file for 4,000 sequence entries, this loop is only going to execute 4,000 times. All right, so that leads to a few changes. First off, we've got the try and except around it. So one of the most obvious things that could happen is that when you try to launch our software, you would give it a file name that doesn't actually represent a file on the disk. So we have our try at the top of this and the except at the bottom of this. And if we try to provide it a file name that doesn't actually correspond to the file on the disk, it pitches out an error, the file was not found, and dies. But in general, the software is simply going to loop through all of the sequence records. Now, you recall that we had some code in there yesterday, 2 days ago, that asked, what is the first character of this text line? You remember that if this line, square brackets 0 equals double quote, greater than symbol, double quote. That was in the code 2 days ago. It's not anymore. And the reason is that the software is parsing all of that for us. So we don't have to specify that information anymore. And because this code is going to execute once for each sequence, every time we go through the loop, we should add one to our counter of how many accessions are in this database. So that if is no longer necessary. Similarly, we had an else in there so that we would evaluate lines of sequence differently than lines of accession. Again, not necessary. Sequence records are not just strings. Sequence records are classes and they have a structure. So you can see that this SeqIO doesn't have open and close parentheses after it, does it? So it's not a method. Instead, this is a field of data. So every sequence entry that we encounter in this FASTA file is going to get, when it's created, when it's read from the disk, it's going to create a SeqIO, a string that represents the whole string of this, the whole sequence of this particular accession. So that's already quite lovely. Now, I noted that before we were looping through every character of the string that we had read from a sequence line. Does everyone remember a little for loop inside the for loop? We no longer have to do that. In fact, we didn't. I only realized after writing that code we didn't have to do it that way at all, because you can pass our sequence. You can pass our letter counts a whole string of sequence at the same time, and it will do all the foring for us. It will already loop through each letter of the sequence without our having to tell it, here's one character, okay, here's another character, here's another character. We can just overwhelm that bad boy, throw out a whole string of sequence, and it will digest it up into individual letters and add them all to the counter. So that's already a little improvement over what we had before. But I would note that we have a new field that we are updating every time we look at a protein. We now have sequence lengths, which is a list. So I think this might be a good moment for us to break over into interactive mode on Python. Is that all right with everybody? I don't mean to just yammer away all class. It's useful if we're actually typing something. So let us try launching Python in interactive mode, so no name of the script here. So let us say that I'll call this my list equals a list, and I'm not going to put anything in it for the moment. All right, so what does my list equal at this point? Just square brackets, right? It's an empty list. Now I'm going to give my list new information through the append command. Everyone see that? Here's sequence length append. We're going to do the same thing. So my list dot append. Favorite number? Who has one? 13. I heard that one. Did I hear a 5?
Yeah.
5? Okay. A 5. Okay, mine is 73. Okay. 7? Just 7. Oof. All right. Any back here? No favorite? Also 7. All right. Well, we'll add it twice. That's cool. 4. 4 is a very good number. Okay. Now let's look at the current value of my list. So my list, every time we've run the append function, has added another item. This is not like a counter, is it? You remember we added the number 7 twice? List remembers each of those separately, and they're in the order that we appended them. So 13 was the first number we added, 5, 73, a pair of 7s, and then an individual 4. So when we come to this code, for every sequence record, we're going to add to sequence lengths the length of the string that represents the sequence. So if you have 53 amino acids in a protein, the number 53 gets appended to our list. So how many different numbers are we going to have in this list? Well, how many numbers are going to be appended to the sequence lengths list for the Mycobacterium tuberculosis database? We've seen this number every day for a little while. It's just over 4,000. I think it's 4,018, if I remember correctly, in the database we're using. Yeah. So every time this loop runs, it's going to add another item to this list. So these lists don't run out of space very readily, right? You can dump a large number of numbers into a list, and it'll just keep them all. And it'll remember exactly the order in which they were passed. So this append code is going to build this. So we're collecting 3 kinds of information from each protein sequence. Well, this would work for nucleotides as well. I don't know why I keep saying protein, but I'm a proteins guy, so we'll just stick with it. So for each protein, we're going to increase our accession count by 1. That's what the plus equals means. We're going to update our roster of how many times each amino acid has appeared in this FASTA so far. We're also going to increase our list of sequence lengths by 1, giving it an additional number. So until it runs out of FASTA database entries to add to our roster, it's going to keep cycling through this for loop. And at the end of the day, just as though we had run the open command, we're going to run close on the FASTA file object that we had created. Okay. I decided that that it doesn't make a lot of sense to view the counts of letters in the order they were added to the counter. There are really only 2 ways that most users are going to care about getting our frequency, our distribution of how many times each amino acid was seen. We want to know what were the amino acids sorted from most frequently seen to least frequently seen, and we want to see the alphabetical sort of them. So we're still going to compute those 2. That's just a resorting, basically, of the counter. All right, we're still going to report how many accessions there are overall. We still want to create a plot of the letter counts sorted in decreasing order. We're just going to show that plot, not the other one as well. You see I've commented out that code down here. But you see I've added some new code down here, and I want to try to walk through what these mean. Let's start by looking at this vector that we'd created in here. So I want to run a numpy. I'm sorry, it's going to stay with me. We want to use functions from numpy. Now, what did we have to do in order to do that? We had to import it. So import numpy. Is that going to behave itself? It is. How nice. Did that fail on anybody's computer? Oh, good. Okay, so numpy is going to give you lots and lots of functions. It didn't work for you. Okay. If you back out of here, well, I don't want to do that just now, but you can run the pip command. I supplied a command in the email that everyone should have received today. Did you receive it? You haven't been receiving any of these emails. Oh my goodness! All right, let's. That is so awkward. Okay, well, I'm going to back out of this for just a moment. So you can just run Python at the command line, right? Okay. We're going to run a -m pip install numpy. Is that visible? Sort of visible. Okay. Python -m pip install numpy. Did I forget anything, Darren? Okay. I'm going to run that command. Okay, on my computer, I already have numpy installed. So you can see that the requirement is already satisfied. Now, Darren helped me with a problem on my desktop computer today where I tried to install numpy and it said it was already installed, but it wasn't fully installed. I had to do a force reinstall on it in order to get it to install properly in the first place. That was awkward. But if you run Python -m pip install numpy, it should add that library to your machine. What's that? Oh, good. Okay. But your machine didn't freak out when you said import numpy? Oh, good. Okay. Well, it may have installed automatically for you. I think when we install matplotlib, it automatically installs numpy. It does not? Okay, well, maybe I'm making things up.
This is no module name install. No module name.
Oh, okay. I think you're missing a letter in here. You're on this one, right? Okay. You type. Okay.
Oh,
you type
I
pip.
did.
Yeah, the word pip is important.
I restarted.
Okay, yeah, so pip is a module installer for Python. It's what we're using to install matplotlib and biopython and numpy in this case. Okay, Grant, I'm going to pop back into Python, if you don't mind. Okay, I had something called myList. It was a list. My list was, I appended 13, I appended 5, 73, 7, 7, 4. My list. Is it the same? 19, 5, 36. Yeah, it looks good. Okay. So we now need to import numpy. And now we have access to the commands of numpy. So let us do this first one, the mean. Any guesses? What mean returns? All right, we're getting an average, right? Yeah, the arithmetic average of these, the arithmetic mean of these numbers. So it's adding together the sum of these. Can I run sum? Is sum a command here? Do I need to run that through numpy? I'm going to just try it. I'm going to be wild and crazy and unencumbered. Ah, there it is. So I can run sum on my list, and I get the number 109. And sum my list divided by the length of my list. Is that going to work the way it should? It is. How about that? Okay. So we're computing a sum for these values, and we're dividing by the number of items in the list. That's great. Okay, so we've been using len primarily for strings. In this case, using it on a list does not return the string length of all of those, right? I mean, that would be 1, 2, 3, 4, 5, 6, and so on. Length in a list says how many items are in it. Okay. So we see that number has an unnecessary degree of precision, wouldn't you say? That's a few more digits than we strictly need to describe that number. So I have added in a function called round. Round is our friend because it's going to make that silly degree of precision seem a little more sensible. Let's say I wanted just 2 digits of precision. You see, I can now get 18.17. If you give this a 0, do you get back an integer? This is a philosophical question. I have now used round, and I've given it comma 0, which means I want no points of precision past the decimal point. So is that an integer? It's not. It's a floating point that has been rounded to the nearest integer value, but it is still a floating point number. All right, that's fine. So in our code, you can see that I have run numpy mean on our sequence lengths. I've told it I want to keep just 1 point past the decimal, and when I do the round, and then I am converting it to a string so that the print command doesn't freak out on me. All okay? Great. Now, I spent a surprising amount of time trying to figure out how to compute a minimum and a maximum. Every other language I've encountered seems to use min as its function for computing the minimum value, and an max if you want to compute the maximum value. It is not quite so straightforward in numpy. If you use min, you will find something for comparing values between 2 vectors of numbers. So it's actually a very overpowered function. A-min and A-max is what you need instead. So the A-min value that we see here is going to compute the minimum sequence length observed in any of the proteins of this. And the A-max is going to be the largest length of any of them. Now, one of the things that we like to do in non-parametric statistics, no one flinched when I said that. Didn't you guys kind of worry about the non-parametric statistics? Well, I'm a big fan of non-parametric. Okay, it's fine, it's fine. So the mean value is lovely, but it doesn't tell you everything you'd want to know about a distribution of values. I like to know where are the middle 50% of those data housed. Between what 2 ranges do we see 50% of all the proteins in, actually the middle 50% of proteins from this database? So we're going to report something better than the mean, minimum, and maximum. We're also going to report the median and the 25th percentile and the 75th percentile. So the 25th and 75th percentile in quartiles are called what? Yes, the first quartile. All right, okay. So if you were to divide the data into quarters, the 25th percentile is that boundary between the first and second quartiles, and the 75th percentile is the boundary between the third and fourth quartiles. The median has a very similar relationship. We could also call it the 50th percentile or the second quartile. It's the boundary between the second and third quartiles. Great. So we can call these last 5 values, minimum, 25th percentile, median, 75th percentile, and max, as the 5-number summary for a distribution. So we want to report the 5-number summary plus the mean because people care about that. Okay, so I've now walked through all of the code. I think having this in front of you is very useful when you're trying to do a bit of statistics on the values that came back. Whatever code you're writing, frequently you're going to want some sort of mathematical characterization that comes out. Having some knowledge that numpy exists, numpy exists, and has all these functions just waiting for you is very handy. If you need to do something like a matrix flip over its diagonal, I'm sure numpy has you covered. I just don't happen to know offhand what those functions are. But because you know numpy exists, it'll be a lot easier for you to find that. All right, let us now come to our command line, exit out of our Python code here, and now I want to run our latest version of the software. So I'm going to type Python the interpreter, today's date, there it is, goal 5. What else do I need? The FASTA, right. So I just type my, and there it is. Anything else I need? All right, let's hit enter. Let's play the feud. All right, so not bad. Pretty quick turnaround. So behind the scenes, we still have the software saying exactly the same thing as it did. This is one thing to remember, that you may change the innards of your code in a way that's invisible to your user and yet add a lot more flexibility, right? We didn't have all that business about sequence lengths in there yesterday. But behind the scenes, from the user's point of view, they don't need to know any of that. So we see that we found 4,018, good memory, sir, different entries in the database. We have this many letter counts, but the software is going to continue only after we close the graph. Now, just to be clear, I was a little bit brusque with my users in this code. I should have listed at the bottom of the text window, please close the graph to continue. Right now, the users don't know what to do, right? Are they supposed to click one of these crazy buttons in order to make the software go on? In this case, we're just going to close it out and we continue on. So these are the letter counts sorted decreasingly by frequency. These are the letter counts sorted alphabetically. Again, I have not protected the user from the fact that these lists, although they're equivalent, just sorted differently, are printed in different formats. If the users wanted to throw this into Excel, would this be a useful export format? Not so great. So if I were being kind to my user, I would probably print these letter counts and frequencies in a little grid format. Say each amino acid on its own line with a count after it. That would be nicer. All right, and so finally we get down to our new code. So we see that the mean of sequence lengths is 333 amino acids. Oh, just to be rude, is that big or small? Small? Why do you say that? I like you, sir. That's a good answer. It's a good answer. I would say it's actually a really convenient number, because how many nucleotides is that open reading frame if it produces 333 amino acids? Did you say 27? 999. Okay. This is a handy piece of knowledge to carry around in your head, because it's a really convenient number. The average open reading frame size in nucleotides for Mycobacterium tuberculosis is about 1,000. Who knew? Right. That is a useful piece of information. So when you're given a protein sequence from MTB and someone says, well, it's 400 amino acids, you can knowledgeably say, oh, bigger than average, isn't it? All right. I get excited about these things. All right. What is the shortest protein in Mycobacterium tuberculosis? Did I give you enough information? Well, we know that somewhere in that FASTA database is a protein with only 27 amino acids. So that's pretty short. How about insulin? Is insulin bigger or smaller? Can someone slam that door? No, just kidding. They're nice folks. I'm glad they're having a good day. Okay, so the minimum, that is, I believe, smaller than insulin. Isn't insulin like 42 amino acids? Anyone know that one? Okay, well, Google will help us. But in any case, we see that the minimum length is that, the maximum length is 4,151 amino acids, which means it's like 12,000 nucleotides long. Isn't that an incredible dynamic range of protein sequence lengths? It's amazing. All right. And then finally, I wanted to ask you about this interquartile information. Specifically, let's look at the median. Is the median length of protein sequences the same as the mean of sequence lengths? It's not. So one of the things that you may begin to suspect is that the protein sequence lengths for Mycobacterium tuberculosis are not normally distributed. We already see that the highest value is way more than the mean value or the median value. How does the median differ from the mean?
Isn't the median the one that's in the middle and the mean the average?
I Yes, it's the one in the middle. So if we were to sort all of these proteins from the very longest, 4,151, to the very shortest, 27, the one that falls right in the middle of that list is the median. So when we see that the median and mean have moved apart from each other, that's usually an indication that you don't have a normally distributed set of lengths. Okay, great. Well, in a nutshell, we have learned how to do things like conditional execution using if, elif, and else. We've learned how to do loops with for and while. And we've discovered that there are an awful lot of ways that you can end up using a for loop within Python, more so than what you see in other languages. We have looked at, maybe confusingly, the difference between a class and its subclass in the case of dictionaries and counters. We've looked at some of the valuable ways that we can employ lists. In the case of our example just a moment ago, recording the list one after the other of all of our lucky numbers in the class. Now we know what to do for the next lotto entry, right? We got our numbers ready. That's good. So lists are these containers that we can keep adding more and more information into and probe with functions like what NumPy has to offer us. So that's pretty great. What I think I haven't left enough time for is understanding how to take a complex problem that you are facing in your day-to-day project and how to decompose that into the functions and data structures that you're going to need to solve it. This is something that does not come easily for people. And on the first day, we started with that flow chart that showed the decisions we would need to make and the small procedures we could follow for individual pieces of that problem. Stellenbosch University is now in the process of creating a school of data science and computational thinking. And one of the skill sets that we model as part of computational thinking is not just abstraction, which is, how do you turn a biological problem into the data that represent that problem, but also problem decomposition. So I, for example, am working with some software called InterProScan that produces a big XML file that shows me things like the gene ontology assignments that are most likely for a long list of proteins. It's very, very powerful. But that output is all jammed into this big XML file, and it's not that easy for me as a human to read that. Now, Python and Biopython have a lot of things that can help me dig into that. It has XML readers out the wazoo, plenty of cool stuff that can handle that problem for me. But I'm still going to have to go through the problem of decomposing this challenge. I've got this big blob of XML, and I want to pull this information out of it, and I want to write it into a table that I can then feed to some convenient software. Right? That's not a simple thing. It's not a one-step process. There's no one-liner to write in Python that generates this table. So the problem of decomposing a complex informatic problem into for loops and into lists and into matrices, if that's what I'm going to require, is something that develops with experience. I want to tell you right now that you know a little bit of Python, you have a lot of power in your own hands. If you face a bioinformatics problem, you don't have to go running to somebody who knows how to program now and say, solve this for me. But you could go to them and say, look, I know a bit of Python, but I'm really struggling to understand how to get from here, the problem as it exists, to the outputs that I want. Can you help me flowchart this out? And I gotta say, programmers are a lot more likely to help you with that kind of challenge than to just write something for you, because programmers are busy people. They're also lazy people, as I've attested many times for myself. So I want to encourage you, as you encounter things that you would like to try, it could be really valuable to you to talk with someone as you try to start a project into how to decompose that into the data structures and functions and so on that you're going to need. And I think most of the bioinformaticists here are willing to help you with that step. It's a lot easier for us to commit to an hour to draw something on the whiteboard than it is to take the time to just write code. So I hope that we can all help you. And I'm really, really grateful to you for sticking through this course for 6 sessions now to gain a little bit of flexibility in how you deal with biological problems. So thank you very much for your confidence in me, and I will be glad to continue working with you guys as you come up with interesting problems to solve. So thank you very much.